The floor is yours.
Okay. Thank you, Andy and Sam, for organizing this, and thank you everyone for turning up. And if you don't, if you'd like to keep up your cameras while I see what you think about what I'm saying, it would be great. So some of you might have seen this part of this talk at the Base for Health conference earlier in September, but this time I hope to give you a bit more insights about what we can do, just presenting a realistic, I'd have to say, data analysis. So I'm gonna give a bit of an introduction of PDMPs and zigzag sampler for those of you who are not familiar with them, and then explain what we have done together with Gareth and Simon and our proposal of making it all automatic. And then I'm gonna go through just one simple example of a survival regression model and how we address the parameter estimation with our zigzag sampler. Okay, let's get started. I'll mainly sort of set the notation and give you a couple of elements of PDMPs and zigzags. So a piecewise deterministic Markov process is a continuous time Markov process, and they're usually used to explore a location of interest xt, and the space is extended with a velocity vt, which helps us to explore this location efficiently. If we want to sample from a PDMP, we need to sort of set three basic elements. The first one is the deterministic part, which is a system of equation that tells us how the system evolves if nothing random happens. So if we're at a time s, we can sort of move forward and see what would be the system at s plus t with no random event happening. Then we have these random events. So we need to define the process at which there are some times and in which the deterministic systems change. And then we need to define a transition kernel to see how the system change at the switching times. I'm going to talk mainly about the zigzag process and particularly the zigzag sampler. So this is a specific PDMP that I've been working on. Again, we're working on an extended space of a location and a velocity, and we are using the location to explore a target density of interest that can be written in this way, where U of x is the sort of potential that will help us in deciding how to move around x. The velocity instead can take values in -1 + 1 to the power of d. And we need now to define the three elements that I talked about before. So the zigzag process moves at constant velocity between switching time, so that the derivative is always equal to this +1 - 1. And we can always project ahead for a time t, where the system will be starting from a point xs vs. The velocity then switches according to the minimum of the non-homogeneous Poisson processes with this rate here, where the important part, of course, is the fact that the rate to switch is guided by the gradient of our potential. So when we will be out in the tail, it will propose to switch back towards the mode. How do we turn back? We apply the flipping operator, which tells us that if the minimum of this non-homogeneous Poisson process is for the dimension I, then that dimension will flip the velocity, changing to +1 or -1 and vice versa. So this is the behavior that we see in practice. So in green, you find the so-called skeleton point, which are the switching times, the location of the switching times. This is a sort of isotropic bivariate to normal, so very easy to explore. And you can see in gray, the deterministic trajectory. And when we go towards the tail in region of high potential, we propose to flip and turn back towards the mode. Okay, so this was just the background to define the notation. How do we make this automatic? Well, first, what do we mean by automatic? We mean that it's something that can be sort of somehow blindly applied to target density that a desired target density. So we have seen these three ingredients, and the really sort of problematic bit is just this non-homogeneous Poisson process. proposal of the switching time. And it's problematic for two reasons. First is that we need this gradient here. And for as much as I do enjoying sort of manually differentiating minus log densities, I know many other practitioners who want to do Bayesian statistics don't want, or sometimes they just cannot because the system is too complex and I've got too many recursive relationships. And then the other problem is that we then need to sample from these non-homogeneous Poisson processes, which is quite tricky. So how do we solve these two issues? The first one, so computing the gradient, well, we can use automatic differentiation, which is very, very good because it doesn't introduce any numeric error. And we have a sort of black box that, given any potential at a certain point, gives out the gradient. So, and then how do we solve the problem of simulating the non-homogeneous Poisson process with these rates? So the first trick that we can do is just to sample from the minimum by sampling from a non-homogeneous Poisson process with the sum of the dimension specific rate, and then sample the dimension to switch with this probability here. But still, we need to sample from this non-homogeneous Poisson process, and what we decided to do is using some thinning, where thinning means that we, since we have now a time varying rate lambda t, we find an upper bound lambda bar. We propose from an homogeneous Poisson process with rate lambda bar and accept the proposed point with probability lambda at t star over the lambda bar. Graphically, it means this. So we have a time varying rate, an upper bound. We propose these green lines, which are from an homogeneous Poisson process with rate lambda bar. And then for each proposed point, we accept with the probability this function of interest over lambda bar. So we eventually accept here at our third attempt. The last thing that remains to do is finding this upper bound lambda bar. And what we propose to do is to exploit locality, to use a local upper bound lambda bar. Hence, we set sort of a tuning parameter T max. We look at the function lambda t between 0 and T max and find the lambda bar that is the maximum of lambda t, the maximum value of lambda t in between this interval. We do this by numeric optimization. So we just run a numerical algorithm that finds this upper bound lambda bar here. And let me just make a side note here. There is some work done, in particularly by Filippo and other researcher about exploiting another way to sampling from the non-homogeneous Poisson process, which implies methods such as numerical integrations. The reason why we decided to go down to the thinning route is that since we wanted something to do sort of numerically and automatically without us looking at it, tools like numerical integration requires you to set a grid on the space and then evaluate the function of interest lambda over all the elements of the grids. Whereas optimization algorithms usually have can be made much, can reduce largely the number of evaluation of the function that you want to minimize or maximize. So we found it much more efficient to run an optimization algorithm rather than an numerical optimization rather than numerical integration. Okay, so we have got all our ingredient. This is the pseudocode. I'm not going to go through it in much details. You might be able to recognize the usual scheme of the zigzag, but the interesting addition that we made is adding this maximization step here at the beginning where we set what lambda bar will be for some points. Of course, if there are no switching between 0 and T max, then we will move the location deterministically to T max and then continue looking ahead of another T max interval and set another lambda bar. Okay, let's now go quickly through the example. I decided to try out on a simple survival regression model for some reasons. First, because I I'm on a Base for Health grant, so it seems sensible to start via biostatistics example. I found a quite interesting data set, which I referenced as well, and I hope you might find it useful because it's a big database on health variables. And second, survival regression is something very sort of easy to understand, and the survival regression model are easy to understand, but at the same time, there is for many survival regressions model, there are no sort of closed form MLEs that helps you speed up the inference much. So it sounded like something on which our method could be used and sort of improved a lot. So as I said, I found this, I made this nice discovery of this simulacrum synthetic data set. It's a data set which is made to replicate the data collected on cancer patients in the UK. So it's synthetic, so you don't have to go through all the fuss of having permission to use sort of identifiable data and sensible data, but still is quite big and quite realistic. So it was made intentionally for people to test their code before asking for the permissions to access the real thing. It includes data on more than 2 million patients and their tumors. And it records many variables, including the time of each cancer diagnosis, the time and type of final outcome, and final outcome can be, for example, death or censoring if the patient is still alive and is being followed up, and basic demographics of the patients and characteristic and histories of their tumors, for example, the time of surgery or the stage of tumor at diagnosis. So this is the sort of the kind of data set that we will work on. So we have TJs, the time from diagnosis to either death, which is either death or censoring. This is encapsulated in the variable CJ, with CJ being equals to 1 for the main event, which is death, and 0 for censoring. As you can see, it's mainly administratory censoring. So these are people who are still being followed, apart of a couple of dropped follow-up. And then we'll have sort of a set covariate. The results that I will present are only on a subsample, on a random subsample of 5,000 individuals, but we are currently working on sort of the full data set. So we hope to present soon some bigger results. I have chosen to start with fitting a Weibull model, which is a model that is usually adopted for survival data. And we are modeling the time to death with this density function here, and then the time to censoring for the people who survived with this function here, with this survival function here. I've chosen a Weibull model because among the parametric survival, it's quite simple, but still quite flexible. It only has one scale parameter and one shape parameters. So we can write down the overall likelihood of the vector of the times and the outcomes like this, so exploiting the two different density functions. And then we want to do survival regression, so the scale parameter will be related via log-link function to a set of covariate of interest. In my model, so I warn you that the results are, well, first of all, they are on simulated data, so you shouldn't sort of give too much importance on the actual quantification of effect, but we also try to keep the number of covariates considered very small to 2, just a continuous and a discrete covariance to just start with the experiments. So in a real data scenario, we probably want to correct for other factors that we know affect the time to death for cancer patient. So we looked essentially at the age of diagnosis of each patient, and then at the spreading status of cancer. So Z2 is going to be equals to 0 if the cancer hasn't spread and it's in stage 2 or smaller, and 1 if the cancer has spread somewhere else in the body, so it's in stage 3 or greater. So the location vector in the sort of zigzag notation that I said before, it's going to be given by the shape parameter, which will be log transformed, and the three betas that we want to estimate. Okay. It's not very important to go through this plot much in details, but we do initial runs to tune the value of Tmax so that it's optimal, and we reduce the number of gradient evaluation that we do. We find pretty easily what's an averagely good value of Tmax, and then we run the algorithm. Okay. So you can see, so these are the 4 parameters, the logarithm of the shape and the 3 betas. And in the 3 betas, you can see sort of the classical zigzaggy behavior with skeletons going from one side of the mode to the other and then switching back. The shape parameter, however, is a bit more, it's not mixing that well. It's a bit moving a bit more slowly. And essentially that is because it is the shape parameter. So it's one that is much harder to estimate and affects a lot the shape of the likelihood. I wanted now to show you something that I find quite interesting. So these are, for the 4 parameters, these are the plot of 10 skeletons of the zigzag run for some switching points, starting all from more or less around the mode. Yeah, I just used them to see what was the sort of posterior distribution, how it came out, and I compared it with the chains of a well-tuned HMC algorithm to see if they led to something similar or to a similar posterior distribution. And it both looks okay. And then I tried and test whether the zigzag algorithm was able to reach the mode even when I was seeding the initial values a bit far away. So without having all the sort of prior knowledge and my initial runs, etc., just sort of blindly say, okay, you go a bit to the edge of the space and see where you go. And I was happily surprised to find that the zigzag is quite robust to not so wisely chosen initial values. And even when, sort of it shoots off, then at some point when it reaches region of high potential, it gets back on towards the mode and then stays there. When I started the HMC on the same initial seeds, it was a bit hopeless. So we've got only one that is actually exploring where it should be. I ran this for much longer than 1,000 steps, but still, I guess the reason why I presented these results is that I could really see the advantages of something that moves continuously with respect to against something that moves discretely. So as I said, even if here we were deterministically moving away from the mode, we were moving somewhere where then we could be bounced back to the mode. This is not the case for a discrete time algorithm. So yes, so the reason why I presented the result is not only because zigzag works and it's good to see that, but also because I really would like to find more and more experiments where this becomes relevant. For example, here I've used only a subsample of the data, so the likelihood was maybe not so picky. I imagined that increasing the sample size to 2 million data sets, the mass would be much more concentrated on the true values, so the possibility, even without starting from a reasonable starting point, but the likelihood of getting towards a mode with very concentrated and high mass would be even more, it would be even more problematic to go there. So if an algorithm is already struggling as HMC seems to, then it would be another sort of another case where something continuous time might be the optimal way to go, or a better way to go. So the other point that I want to make is that I haven't yet tested. So at the moment, I've tested my standard zigzag algorithm against some well-tuned HMC. I haven't tested any fancy HMC, as in something like the non-Newton sampler that is implemented in Stan. My impression is that, for example, things like these will be solved in something more adaptive, like the non-Newton sampling. But again, as I'm using a pretty rigid and sort of basic version of the zigzag, it seemed fair to sort of limit my comparison to that for now. So I think there is a lot more to explore. Sort of we're looking into a way also to boost the automatic zigzag and see if we can have a sort of improved version or something better to compare with really what's currently used by practitioners, that is in fact something more similar to Stan. Okay, I don't know how I did with time, but I'm now okay. I'm now on just my concluding remarks. And so again, for the people who have listened to this talk twice, there is a manuscript in preparation, and it's going to be, we hope to put it out in a month or so, well, in the next month, this or next month, and to submit it. And we are currently working about how to exploit subsampling techniques, which are really the sort of the power of the zigzag algorithm and other PDMP-based samplers. It's not so tricky. It's not really so simple, above all because we want to still stay in our setting where essentially nothing is known apart from this U of X. So since this subsampling techniques is really based on the availability of the upper bound, is being a bit tricky, but we have some ideas. So we're trying to develop these points. And then we want to explore some recent ideas that can be combined with our automatic way of deriving the rate and bounding. Of particular appealing is the adaptive skin by Bertazzi and Birkens, which essentially gives you a way to match, gives you a routine to match the velocity to the target density so that it performs as well as a zigzag sampler would perform on an isotropic Gaussian. And I think this is particularly appealing for our method because we only have one tuning parameter, the Tmax, which might be in a sense optimal for one dimension, but not for the other. So reaching an homogeneity in dimension would improve a lot, I think, our algorithm. And then this is just really a discussion point rather than a conclusion. Filippo gave a seminar in Warwick a few weeks ago about the quantification of the error of his numeric zigzag algorithm. And he has many ideas on how to as well explore the error that I might have introduced with the numeric maximization in my method. And so we're looking forward to work together on this. And I'll welcome any questions or comments that you might have. Thank you.